Let's take a look at a problem where we have a ball on a string and the ball and the string are rotating around the y-axis right here. It's not going back and forth like a pendulum, but it's rotating around the y-axis, even though it might look like a pendulum, but it's actually rotating around. All right, so what would happen if someone were to pull up on the cord as it's rotating? What would happen? We're going to assume that the ball goes outward and that this length becomes smaller, obviously, and that this angle becomes greater. We're going to assume that this angle has become greater than that angle. So we have a length 1, we have an angle 1. As the ball is going around, we're going to pull up on the cord. That's going to change the angle. It's going to make the length appear to become smaller. This particular length becomes smaller. So we're going to have a length 1 or length 2. We're going to have a theta 1 and a theta 2. So we're going to assume that theta 2 is greater than theta 1, and we're going to try to find theta 2 through the means of through our means of finding out what the forces are in x and y direction. That's the easiest way to find this particular theta 2. So let's look at this. Let's see what happens in the forces in the y direction. The forces in the y direction are going to be y and some tension. There's going to be some tension in the cord, and this is also going to be length 1. This will also be length 1. We are going to say that the cosine of theta 1 is going to be equal to what? Adjacent over hypotenuse, which would be our weight divided by our tension. Therefore, tension times the cosine of theta 1 minus the weight is going to be equal to 0. We're going to assume this to be true. All right, there's no energy in, no energy going back out other than the weight and the tension. There's nobody's pulling on the cords, nobody's like messing around with these cords and making it go faster or anything else. We're just going to assume that the energy, no energy in, no energy out. So this is going to be true. It's going to be our forces in the y direction. What happens in the forces in the x direction? Well, in the x direction, you don't have to worry about weight, but what we do have to worry about the weight. What's going to happen with the weight on this side is going to be an acceleration on this side because of the centripetal force. The centripetal force is going to be on here pulling on this ball, and the ball is going to want to fly out this way. The faster you move this thing, the faster it goes around here, the more it's going to want to fly off. All right, in this direction. Even though the acceleration is pointing in this direction, the ball is going to want to take this it's going to want to go in this direction. All right, so what is my accelerational force? It's the centripetal force is going to be equal to what? mv squared divided by r, right? Well, let's define r. Isn't r going to be the sine of r is going to be r over t? So therefore, r is going to actually equal to L over sine theta. Right? Isn't the sine theta going to be r over L? Sure, that's what it's going to be. Well, we can plug that in here. So this is the acceleration centripetal is going to be equal to the mv squared divided by L sine theta 1. Hey, that's good. So we define what's going on in this direction in our y. Let's see how it's related to t. Well, it's going to be related to t through sine, obviously. So the sine of theta 1 is going to be what? Opposite. Sine is opposite over hypotenuse, so that's going to be mv squared divided by L sine theta 1 divided by t. Okay, that's the definition of sine. So therefore we can bring the t over here. So we're going to have t sine theta 1 is going to be equal to mv squared divided by L sine theta 1. Well, let's multiply both sides by L sine theta 1. You're going to get L times t times sine squared theta 1 is going to be equal to mv. E. This is a stopping point. We have a mass here. Well, how can we get rid of this mass? This is going to be kind of in the way. We don't need it because we don't have any mass on this side that we can cancel out yet. Well, let's take a look over here to see the definition of what t is. T in this case is what? T is going to be equal to weight divided by cosine theta 1. Right? Can we put that in over here? Sure, why not? So we have L times the weight. What is the weight? Isn't the weight equal to mg? Whoa, mg, this is what I love about physics. Mg divided by cosine theta 1 times sine, where I got a, yes, squared, yes, there's a square there, sine squared theta 1 is going to be equal to mv squared. Whoa, looky here. We can get rid of that mass. Isn't that great? Isn't that fantastic? All right, so what's cosine divided by one of these sines? That looks like a tangent to me. So we're going to have a square root then. So we're going to have L times G. We're going to have our G here times sine theta 1 tangent theta 1 square root is going to be equal to our V, our V1. Whoa, really? Is that what it is? I think it might be. We've just found the equation for the velocity of a ball that's rotating around the y-axis. This is going to be its velocity. All you need to know is the length and the angle. So you need to know this length and this angle, and you can know the velocity of that thing. That is amazing. I'll let you take a picture if you like. That is truly amazing. Now the next step, how are we going to relate that to the ball that when it gets up here? How those two are going to be related to each other? Well, again, you're going to have to use the Fy forces in the F and Y direction, but let's think about it another way. There's no energy coming into this system, and there's no energy going out of this system. That would mean that the mass times the R1 times V1, that's this thing right here, is going to have to be equal to the mass times R2 V2. Is that not true? Isn't it true that the law of conservation would say these two would have to be equal to 0 since there's no energy in, no energy coming back out? I'm thinking it is. If it isn't, leave it in the comments and I'll see if we can work on that. But I'm pretty sure that's going to be the case. If that's the case, we already know what R is equal to. R is equal to L sine theta, right? And then we'll call this sine 1. R2 is going to be what? L2 sine theta 2, right? Well, we can put that in here, right? We already know we already know the velocities. The masses will cancel; they never change, but these might change. But let's see how this is related. That would mean that R1. So we're going to put R1 up here. R1 is L1 sine theta 1 times the square root of L1, right? L1 G sine theta 1 tangent theta 1 is going to be equal to L2, hope I have enough room, L2 times because this is our R2 right here. We're going to be looking at this one, R2, L2 times sine theta 2 times the square root of, hope I have enough room, L2 G sine theta 2 tangent theta 2. Wow. That means these two have to be equal to each other. I think we can solve some stuff here. If we know some of the stuff over here, we can solve for this theta 2. And that's the thing we're looking for, this theta 2. Probably the best way we could do this is to factor out a sine. Factor out let's factor out the L2 and the G. Let's factor out the L2 because we have an L out here and we have an L in here. Let's factor out the L's and we'll factor out the G. All right, so if we have L1 times sine theta 1, if we're going to factor this L1 out, it's going to be L what, to the 3/2? Is that correct? Or is it going to be L to the 1/2? I think it'd be L to the 1/2. And then we're going to have G. We're going to factor out the G. So there's G to the 1/2, right? And then we're going to have sine theta 1 tangent theta 1. Well, we can do the same thing to the other side, I'm hoping. I hope so. We can factor out L2 sine theta 2 L1/2 to G1/2. Gosh, I need a bigger board. Divided by, the square root of sine theta 2 tangent theta 2. All right. I think I can agree with that. Well, let's look at this. If we multiply 1 times 1/2, then we get to 3/2. Now we're going to have, what, sine theta 1, L1 times L1 1/2 is going to be L to the 3/2. Does that sound about right? And our G halves are going to cancel out, so they're going to be gone. They cancel one another out. We're going to have a sine L 3/2 times this sine theta 1 tangent theta 1 square root is going to be equal to what? L2. These two are going to be multiplied together, so we'll be adding it. It'll be 3/2 sine theta 2 times the square root of sine theta 2 tangent theta 2. Sound about right? I'm hoping I'm on the right track. Let's see here. Well, we are going to what? Square both sides to get rid of these square roots, because I don't like square roots. They drive me crazy. I'm not a mathematician. Square roots are kind of like, please get away from me. All right, so let's take the square of both sides. So now what you're going to end up with is what? L squared. If you square this, it would be L cubed. So you would have sine squared theta 1 L cubed. This thing goes away, so we're going to have sine theta 1 times tangent theta 1, right? It's going to be equal to, how? L, we're going to square this side, so this would be L1, this would be L2. We're going to be to the cube because we're going to square that. Sine squared theta 2 times sine theta 2 tangent theta 2. Boy, I hope you're staying with me, because it is going to work out. It's amazingly beautiful. Actually, to me, this is artwork, but whatever. All right, so we're going to end up with sine cubed, right? Because we're going to have a sine times a sine. That's going to be cubed. We're going to have a sine times another sine over here. That's going to be cubed. So it's going to end up being L1 cubed, right? Times sine cubed theta 1 times tangent theta 1 is going to equal to L2 cubed sine cubed theta 2, right? This is a cubed. Tangent theta 2. Okay, so this is the relationship between the two instances. This thing right here is the relationship between the two instances. The relationship between this instant and then this instant. This particular equation is going to tell you what's going on between these two instances. Well, let's just put in some numbers just for some fun. We'll say that theta 1 is equal to 35 degrees. And then we're going to say L1 is equal to 0.8 meters. And then we'll say L2 is equal to 0.6 meters. All right, these are things that can be actually measured. That's not something that's not impossible to measure. This would be the easiest to measure. This might be a little bit more difficult to measure, but you could measure it. You can measure this angle pretty easy. And then depending on how much you pull up here, that's going to make the difference between L1 and L2. Anyway, so if we put these numbers into this thing, right? We put these numbers into this thing, it's going to look a little scary, but 0.8 cubed, right? Cubed times sine cubed of 35 degrees times tan 35 degrees is going to be equal to 0.6 cubed times sine cubed theta 2 times tangent theta 2. All right, so we got our numbers in here. Now we got to solve this thing. Okay, so I'm not a mathematician, but this is what you're going to end up with. You're going to end up with sine cubed theta 2 times tangent theta 2 is going to be equal to approximately 0.313196 497 blah 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 blah. All right. Alrighty. Now, being a non-mathematician, I took this to I used Mathway to figure this out because I mean I don't know if you can do this, that's great. It's fantastic. I mean I don't think I could attempt it to try to figure out what theta is in this case, but I used Mathway. So when I used Mathway, and if you know how to do it, please leave in the comments how you would solve this thing, because I'm not sure how to do it. Would be equal to, I came up with Mathway came up with 43.63 degrees. There, this is theta 2, is our answer. Amazing. Totally amazing. I mean, just from a little bit of information, a tiny little bit of, a small amount of measuring, a tiny little bit of measuring, we can figure out what the difference is between the two angles. And lo and behold, angle 2 is greater than angle 1. Not by much, but it's still greater. Less than 10 degrees, but it's still greater. So this ball does move out. As you pull this cord up, the ball will move out, right? And this angle will become greater. This length will become less. So this is the answer. I hope this can help you. If you would like, if anybody knows how to solve this thing, please comment. I'm not sure how to do it. I used Mathway. I'm not even sure how I'd even attempt it. But I really appreciate your time. I hope this can help you out. And please subscribe.